off the screen. Hello, everybody. Today you're going to hear about a world champion robot boat. But before we do that, I want to give a thank you to the Herbert Wertheim College of Engineering, to Dr. John Harris, the chairman of the Department of Electrical and Computer Engineering, Dr. David Hahn, chairman of Mechanical Aerospace Engineering, who, without their support, we couldn't do this. We couldn't win world championships. And John, can you come up? This trophy is going to eventually go to Dean, and both chairmen are going to get this trophy. Hold this for a second. And I only have one so far. It's 3D printed, and it says World Champion 2016 Maritime Robotics Challenge, UF's Herbert Wertheim College of Engineering's Navigator Autonomous Maritime System. Thank you very much, John. There you go. Thank you. Okay, and that's 24 karat spray paint. Okay, and the other thing, so when we, right after the competition, we got back from the competition, we watched the Super Bowl. And in the Super Bowl, New England Patriots won their 5th Super Bowl. And they were talking about 5th World Championship. And they all get rings. And I thought, well, that's really cool. So we have a gold ring that all the students are going to get this gold championship ring. But I only got one. So Andy Gray is the team leader. And so Andy, here, championship ring. No diamonds, just gold. Okay, next slide. Okay, so we've been doing robot. My lab is the Machine Intelligence Lab, and we'll hear about another lab that's involved with the project as well. But we've been doing robots in the Machine Intelligence Lab for, well, our first competition was 1998, 20 years ago. And in that, we have this submarine right up here. This first one is got an inverted salad bowl on the top. And that salad bowl had a cork in the top, and we could pop the cork and let it fill with water, and it would sink. Or we have 2 air tanks in there. We can push the water out with air, and it would slowly rise. And that's how we went up and down those first couple of years. We had 4 motors on it. It was okay. Well, we moved on after that. We made a kind of a boxy robot with 4 thrusters. We now would push ourselves up instead of using ballast. Then we made this big robot around 2000. We used that for several years. It's 6 feet long, was aluminum welded infrastructure, and then we had sheet metal welded around it. 185 pounds, 6 trolling motors, 5 motorcycle batteries, and it could pull you faster than you could swim. We went about 50 feet deep with that. Really good sub, but we keep progressing. Then we built this, what we call the flying sub. It looks like it could fly through the air as well as underwater, and it was actually about the worst sub we ever built. But then the following year, we made our first world champion. This 2005 robot is a carbon fiber exoskeleton, and the hull is transparent plastic, so the cameras can see right through it. So all these robots, everything we do in our lab is completely autonomous. There's no remote controls behind the scenes. We call those stupid machines and smart humans. Our smart humans do the work before the robot goes in the water. And then we kept going. So we won with this plastic carbon fiber sub twice. World championship, beating MIT and Cornell and all the other great schools that are out there, and schools from all over the world. I think, what was there, 11 countries last year, or 15 countries, something like that. Big competition, 45 schools last year. So then this sub we won again. We made a sub now is aluminum, metal, so we can kind of a professional sub as opposed to these kind of plastic amateur subs. And we won again, so 3rd year in a row. But this sub was now all built around one sensor, that very expensive sensor that we keep moving from one sub to the other. And then after winning with this one, we built this sub in 2011. This sub had some, it was really another jump, big jump in our subs. This sub had 6 thrusters. All the subs before it had 6 or 5 or less. This one had 8 thrusters, because when we ran with the sub the last one that won, one of the thrusters went out at competition and we're dead in the water. So now we've got redundancy. We can lose a thruster and still the sub figures it out and keeps going from there. Then after that, the only problem with this sub, it was kind of big. Now, it was meant to do not just competitions, but to do research. It went out to the Gulf of Mexico for experiments several times. 3 students have gotten PhDs with work that they did on this sub, controls mostly. And so that was a really good sub, but we had a need to get lighter. And so lighter makes it easier to carry around and gives us more weight to add more things because there's a weight limit at the competition. So we made this sub right here, this Subjugator 8 we call it. Subjugator 8 was made to be easy to add more components, actuation and sensors. And we've added several things since we got it. So this is now about 80 pounds. This guy was about 105. And so we keep progressing with subs, and we're going to probably build a new sub next year. But let's keep going. Then we did boats. Well, before the boats, we actually did some lawnmower work. But it wasn't an international competition, so it's something I don't talk about much. Except that as soon as the lawnmower competition was canceled, we jumped on the boat. We took all the electronics from the lawnmower and put it on this first boat, and we won another world championship. And it's got some temperature sensors. It has a landing pad to land a copter on it. It had some little Nerf gun shooter, and we bumped things, and we have lasers on this, LADARs. So it was pretty sophisticated first attempt. But it wasn't much of a boat. So the next year, after we won with this plastic, really it was made for a chair, a little lawn chair that could be in the water. So you can have your cold beverage in one of these pontoons. And then we added our own electronics to it. We took the chair off, and we went with that. But then we wanted to go fast, so we made this hydrofoil, which could go through the water probably 5-10 times faster than the other one. And it was pretty impressive. And then we heard about another robot competition, and it's called Maritime Robot X, which is Maritime Robot X Challenge, which is what we entered in December that we're going to talk about. And that's the boat right here. So what happens to our students after they do robots? Well, they get the jobs they want. Some of the first places our students went, even 20 years ago, Harris. Harris is our biggest sponsor, and they're also probably have 25 of our tip-top students, especially from a while back, in a lot of electricals. And now they're managers, and so they keep giving back. You know, it's really good. You become famous and rich, and then you give back to the University of Florida. And Lockheed Martin, they've also supported us a long time, and they've got a bunch of our students. Northrop Grumman, they've given us some recent support. We got students at Sandia National Labs, some students from Mill and SIMAR, and other labs too, NAVSEA, Panama City. We've got probably another 25 there. Bunch of PhDs, master students, and undergrads. And then some of these other companies you heard, all of these are places that multiple UF Mill students have gone. Then the companies that maybe you more want to work at now are Uber's. Uber Robot Car. One of the guys that started that was a guy from my lab, worked in my lab before. And then another company you may not have heard yet, but a lot of the Uber guys went to Aurora Innovation, and another one of my guys started that, was one of the starters. And Google Robot Car, which is now called Waymo. Again, a bunch of my guys were there. Now they've started their own companies. 5 years ago, everybody wanted to go to SpaceX, so we got a bunch at SpaceX. Several of the students here have done internships at SpaceX. Peoria Robotics is a local company started by my students. CPAL is a new company. It's actually called Scubotics. CPAL is their first device, started by one of our students. Actually is in a competition this month for getting funding for it. And Amazon, it's another big one that some of our students have gone to. So the students go kind of where they want. But now you want to hear other things, so let's go now. Dr. Crane. Dr. Crane, he's going to talk about SIMAR, which was a partner with us. See, here's SIMAR, and here's Mill.
So I'm not going to talk really long, but just to give you a little background of the kind of work that we've done over the years. The timeline, I've got it going from 1990, and actually should go a little further, but it's nice to see a long history of stuff, but it also means that you're getting old. We lost our most honored guest. So the kinds of projects that we've worked on, these are all related to autonomous navigation. And if you look at the older ones, the ones marked 1 and 2 that were back in the 90s, that really was sponsored by the Air Force. That thing number 1 was an autonomous small excavator, well, not small, it was an autonomous excavator for repairing runways that had been damaged. The Dozer had all kinds of crazy applications for the Marine Corps. And then on 3 and 4, what happened is they wanted to, again for the Air Force, they wanted to look for items that were underground. So we're pulling magnetometers, in other cases ground penetrating radars, so they could clear out some things. And then in the 2000s, so 2004 through 7, the pictures I've got are, if I can read the numbers here, 5, 6, and 7. That was the DARPA Grand Challenges. So in those events, the first two, there's a brown vehicle on number 5 and the blue one up above, number 6. They were similar events just because in the first competition nobody really did that well, and so they did the competition again. And the idea behind that was they gave us data points along a course, a bunch of latitude, longitude. It was about a 150-mile long course, and whoever could do it the fastest would win a $2 million prize. And if you came in second, you got 0, and third, of course, you got less than 0, I guess. What happened in the first year was they invited 43 teams, and 23 teams made the finals. We made the finals. No, I'm sorry, 15 teams only made the finals out of 43. The performances weren't that great, it turned out. And of the 15 teams, 5 got about 5 miles, 5 got about a mile, and 5 of the best 15 self-destructed at the starting line. They basically just died, or they went straight and ran into the wall. We turned about to be in the middle packs, which means we got about a mile, which I was more than happy because I wanted to, at minimum, is get out of the starting gate, take the first corner, take the second corner, and then you couldn't be seen anymore. And then whatever happened, happened. So part of the reason the performance was like that, though, was that we didn't have much time. We were admitted into that competition in December, and the competition was in March. And we did have a lot of experience, if you look at the timeline, with the work that we did with the Air Force. And but still, to pull that off that quick was pretty tough. So DARPA did it again. We changed vehicles to that Blue Bars vehicle, and the same idea, given a bunch of latitude, longitude, who can follow that course and get to the fastest, get $2 million prize. And in some respects, I feel that was our high water mark. We had a really good system. 43 teams were invited to the sort of the trials. They had a trial course. Once you completed the trial course, you'd get into the race, and it was the best time, and that it was tell us when you want us to run at the trials, otherwise we're going to be at the hotel. So we actually had the thing working before we got there, which was very nice. Maybe I was a little naive because we were one of the 23 invited into the finals. They would start a robot once every 5 minutes, and perhaps I was a little naive. I really thought we were going to complete the whole course. I didn't think we'd be the fastest unless some of the big name teams I thought were going to push each other too hard and might screw up, and we'd be the Turtle, you know, and come in. And the Turtle, our fastest speed was like 35 miles an hour. We had it geared way down. That's all it could do at max. But it turns out that we got 14 miles down the course, and our GPS pretty much went out. It went from it having 3-centimeter accuracy to it was 8 meters off, which is ridiculous. And when that happens, you're pretty much at the mercy of whatever happens. But it was a great system. And then the next one we have is the Toyota Highlander. It's in picture number 7. That's down in our lab in 131. It basically could drive in environments like on campus. Again, completely autonomous. So if you're given a roadway definition file and then a mission file of places to visit, it had to plan its route. And it was much more complicated because you had to stay in your lane. Other vehicles are out there. You know, plan your route, react if your route is blocked, things like that. It was much more complicated. And again, the best performer, although the metric to measure it wasn't quite as easy as who got there the fastest, the best performer would get $2 million again. Yeah, we did okay, but again, we didn't finish in the money. The other pictures I just wanted to show that are in the timeline, number 8 is again back for work with the Air Force. They were clearing up some land and things where they do practice training type operations. And now I've got in picture 9, I've got the Toyota back out there because the Toyota's coming back to life. We've got projects with Florida Department of Transportation where they're looking at how autonomous vehicles are going to impact the highway system and the traffic flow and all those kinds of issues. So we're bringing it back there. So if I go to the next slide, this is my last slide. I thought I was only going to talk for a minute, and I get carried away when I see all these pictures. But it's more than just a bunch of engineers. I mean, it was fun and things, you know, to build these systems. We bought that Toyota. It was a brand new Toyota, and we've got students, a lot of them were undergraduates. I mean, this is a brand new hybrid, you know, that we paid a lot of money for it, and we're drilling holes in it and stuff. It just had a funny feeling to it. But if I look at the research components, the things I'm really most proud of in the lab, well, the first two are related to the vehicle work, but adaptive planning framework that really came from the Toyota Highlander. It was, how does the vehicle decide what behavior is the most appropriate behavior to do? You know, should I change lanes? Should I U-turn? Am I getting near an intersection? So I have certain things I need to do when that happens. So that's something I'm real proud of. This JAWS, Joint Architecture for Unmanned Systems, we played a big role in. It's basically an architecture to allow messages to be sent between programs that are running on different computers. And it's the backbone of getting the systems to work. Right now, we're actually very similar to that as ROS. So a featured robotic operating system is very similar. And there are certain advantages to it. So we are looking at ROS, of using ROS. And the last one I listed, it's really not related to autonomous vehicles, but this theory of kinesthetic control is something I won't make a long story about. But if there's anybody here, oh, I didn't tell my robots class that we were doing this today. I say if there are any of them here, they're going to hear about it on Friday. But that's our sort of background and you know, what we kind of bring to the game is that experience.
Good afternoon. My name's Andy Graham, PhD student that works in the Machine Intelligence Lab. So I was the team leader for Team Navigator this year. But I want to talk about the original Robot X competition, which started in 2014. And the objective of the Robot X Challenge was to inspire the next generation of students with a STEM-based, so science, technology, and math, STEM-based competition. And it was held in Singapore. And it's a biannual, so the next one will be 2016. Singapore, which is a kind of enclosed bay that was mostly fresh waters, but it was mostly shielded from currents and winds. And teams were given boats, so there was 5 countries represented in this competition, three teams from each company, and they each got a platform, the WAM-V, which are these 2 pontoons with suspension system. The teams were required to outfit it with sensors and batteries and motors, and so it didn't just work right out of the box. But it was a very high-profile event. They actually had ambassadors from all the countries that were there. It's kind of a political thing. It was also a unification of Pacific Rim countries kind of objective too. So there's some other underlying things going on there. But first year went off pretty well. In the competition, the students were supposed to develop this platform that could autonomously navigate through some obstacle courses. So here you can see some large buoys and tower buoys that they had to avoid. And this is all autonomous, so no remote control. They're also required to dock with inside of a slip that was represented by a specific shape. So perhaps, you know, dock in, maybe it looks like they're going to dock in this circle slip in this one. And they'd move these things so it wouldn't be like, oh, always park on the second one. Another challenge they had was a tower buoy that had an LED screen on it. And that LED screen changed colors. So the boat first off had to find the tower and then report its colors. And it changed colors, and they're random each time. But it had to report to the course coordinator, oh, that was red, green, blue, or is that red, blue, red? And so on. The last challenge they had in 2014 was an underwater challenge where they had an underwater pinger, so an acoustic pinger. The boat had to identify which of the 4 buoys over here had the pinger report its position to the course coordinator, and they got points from that. 2014, MIT won, so they beat everybody, and they started talking about the next competition. In 2016, they said, you know, Singapore was really nice, but it's really difficult for a lot of the teams to get there. Most of the teams a lot of teams were coming from the United States at this time who were expressing interest. So they decided to move it to Oahu, Hawaii, where it would be a little bit easier, especially for ONR representatives, because they had to fly everybody out there. But I'll show a quick video of kind of an intro of what this competition was about.
Aloha and welcome, citizens of RoboNation, to the biggest and most spectacular of our autonomous vehicle competitions, the second biennial Maritime Robot X Challenge.
In 2016, the competition has moved from Singapore to the fabulous Hawaii, on the beautiful island of Oahu.
The first Robot X was an invitation-only competition, but this year the field was open to any university across the globe that wanted to step up to the challenge and field the required WAM-V boat.
So we're delighted to have 13 teams here from Japan, Australia, South Korea, Singapore, and the U.S., including a home team from right here in Hawaii.
I think it's really great that we're hosting this competition in Hawaii. It's been really awesome being able to see all of these different teams here from all over the world, and I'm so proud to have them here at home in Hawaii and be able to share all we have to offer here.
We're really excited to be here in Hawaii. What's not to love? You can surf, you can ski, you can go skydiving, you can go ride in a helicopter, as I did yesterday, to see our huge, beautiful course out here.
It's also the first time in the history of RoboNation that robots will be competing in a true open ocean environment. And we know that nature can make seafaring a difficult and dangerous job.
Singapore was a freshwater environment, it was a confined area, it was a reservoir. Here we're essentially in open water, it's salt water, so we're subject to tidal currents, we're subject to wind, we're subject to different sun conditions that affect that in different ways.
So the real technical challenge here is having multiple issues happening at once and not knowing what those issues are going to be. The environmental sea state can really affect your field of view that you were planning on having. So a lot of these little things can add up to a really technical challenge.
Every team starts with the exact same base platform, the WAM-V, which stands for Wave Adaptive Modular Vessel, a cutting-edge surface vehicle specifically designed to keep its payload steady while traversing rough ocean waters.
The boats themselves are eco-friendly in the sense that there's no fluids on board, nothing to spill. They're all electric powered with closed systems. They're lightweight, easy to assemble, easy to ship. Really an effective vessel for ocean research, reef research, that type of thing.
One of the best things about the WAM-V is its robustness. At first glance, you see the two inflatable hulls, and you think, wow, this thing really can't do anything too crazy. But we've had zero stability issues. It has stood up to the task.
Teams must then design hardware and software that can direct the robot through the varied challenge course, with tasks including obstacle avoidance and search and recognition both above and below the water.
In this competition, one of the courses will be to avoid the obstacles in the sea. So basically on our boat, we integrate our laser scanner, cameras, and some other devices to sense the environment. Then we have our onboard computer to perform the algorithm to avoid obstacles in the sea.
We've built some hardware specifically for this competition. We've got a underwater vehicle which attaches to the lower deck of our boat and lowers down under the water, has the ability to propel down to the sea floor. It has some sensors so it can tell how far off the sea floor it is. It stays generally below the boat, but it has the ability also to venture out.
The teams have worked incredibly hard and put their best efforts into tackling the difficult ocean course.
So check out robotx.org to see which team takes home the title of Ultimate Robot Boat.
That was a brief summary of the competition. So this is Sand Island where it was held. We had all of the student tents up here on the northwest, eastern northern side of the beach right here, and then the competition was held in. And one thing I want to point out, when we first observed this, we thought that this was land here, that the water did not go over that, but it really does. So we experienced currents going, ebbs and flows through this direction. Also, this island right here doesn't have very many buildings. I think there's maybe half dozen houses. So we got winds that were pushing us this way and that way. So it was a really tough environment. Some of the new challenges and changes they made to this year's competition. First one was the shooter task. So there was a four-sided obstacle or buoy that had colored shapes on it. So the boat had to first find this thing, then identify which shape, and it was given the shape ahead of time, which shape to shoot on. And then we had two options here. We could shoot into the big square or the little square, and we got more points for the little square. So the boat had to do all this autonomously. They brought back the docking challenge, but this year they added colors. So they could have three shapes that were all three different colors. So your boat had to be sensitive to colors, which is actually pretty challenging, especially with an environment where the light's changing, such as a cloud goes in front of the sun. The buoy, the changing color buoy was brought back again. Now this year they did something also different compared to last year. Some of these challenges would lead to the other challenge. For instance, if the color sequence was green, red, blue, they may say, hey, the first color is the color of the slip that you have to dock in. So it's kind of like a Scantron. If you start on the second bubble on your Scantron, then the following bubbles will all be wrong because you're off by one. So it made it much more difficult than previous years. Another challenge they had that was different, they actually had objects underwater. So they gave us search areas. There's 4 search quadrants where we had to go and find either a circle or a cross or a triangle, and they looked like this on the bottom. And this was really to inspire, they wanted to encourage student teams to develop this autonomous underwater vehicle or some sort of deployable system so that they could go down and identify it. And when they started mentioning these things and we were starting like, wow, we got a pretty big boat to work with, we decided to partner up with SIMAR at this time because of their experience working with larger vessels and multiple platforms at the same time. Here's our leaders. So myself and Dan are the two team leaders. And then I want to point out something here. So Matt Langford, Lucas Murphy, and Matt Griesler, they're all undergraduates, and they're also our mechanical, software, and electrical leads. And then with that, I'll have Lucas kick it off on the mechanical side.
As Andy said, my name is Lucas. I was the lead mechanic for this project, and this is the rest of the mechanical team for Navigator. So going through the mechanical overview of our vessel, the theme of our design process was simplicity. Our goal was to first find a solution that could be implemented as quickly as possible to get us testing in the water sooner, and during that stage, iteratively refine our design until we arrived at the final designs you see in the pictures of our boat today. The computer box and our sensor mast exemplify this design mentality. It started as a very humble plywood structure that, while it wasn't very robust or waterproof by any means, it allowed us to get testing in the water within a week of us receiving the boat, which was incredible. And then over the following months, we were able to refine our design and come up with this rigid aluminum structure that you see today, while still, throughout that entire development process, having something that allowed us to test in the water continuously every week. And now I'll hand it off to Sylvie.
Hi, so as Lucas was talking about, we got the boat in the water within a week of receiving it, and to do this we needed, we just put it on a piece of plywood. Go to the next slide. So this was our original structure for holding all of the electronics. This made it so that the boat could get in the water and they could remote control it and have the vital sensors mounted to it. But this structure, we had to put it up on the boat, take it down from the boat every time we went out to test, and it was a big pain, and also the screws that were put into it were too long, and so if you put your hand under it, you'd get stabbed. So my summer project was to replace this structure with a more robust, permanent structure that could stay on the boat even when we were towing it down to Lake Walbert for testing every day, or every weekend. So I started looking into IP66 rated electronics boxes that we would have to waterproof all of the connections for, and the only things that were large enough were in the thousands to $2,000, and so we decided to start thinking outside the box. And one of our, Dan had the idea of using a cargo roof box, and so a lot of people thought it was crazy, and I started looking into it further and found out that maybe this isn't so crazy, and people still thought we were crazy. But we ended up ordering it. It was only about $300, and I outfitted it with all the electronics, made it really robust and sturdy, and that's what's on Navigator today, and that won a national championship. World champion, sorry.
And I'll briefly go over our thruster configuration. It was inspired by what we used on Propagator. This was our first entry into the Robo Boat competition in 2013, in which we placed first. It's a very simple 4-thruster configuration. They're fixed in an angled pattern, almost like a diamond shape. And this allows us to have full holonomic control, meaning we can strafe, we can rotate in place, have full degree of freedom on the surface of the water, while having a very simple mounting solution. The thrusters don't have to be actuated in any way. And this is what we adopted on our on Navigator with trolling motors.
Hi, so I worked on the racquetball launching system for the Detect and Deliver challenge. And next slide. And so it utilizes 2 of the same trolling motors from Propagator 1 to propel the ball into the goal. And we used these motors because originally they were on hand. We had them from Propagator, and we used them for prototyping, but then we realized, hey, these actually really work. They had the speed that we needed, they were readily available, and most importantly, they were already waterproof, which was a big issue for us on the seas. Next slide. So the system also uses a detachable magazine system because during our testing, we really wanted to be able to go through as many racquetballs as we could to optimize our testing time. So I developed this magazine system that we can pull off and replace really rapidly. Next slide. And speaking of prototyping and testing, this system has gone through over 15 iterations to find the perfect design so that we can win a world championship.
So part of the competition, obviously, there was all of the obstacles and different structures on the course. And in order to test the actual boat, we had to take all of these obstacles and put them out on Lake Wahlberg and bring the boat out there and test it. Even though a lot of testing could be done in the lab and computer simulation, the actual real-world testing turned out to be really valuable because a lot of the other teams couldn't handle a lot of the different weather conditions. So building all these obstacles, it is a bunch of PVC, different plastic sheeting, pool noodles. It looks pretty simple, but coming up with these designs was actually kind of difficult. So they gave us the specs of what they're actually going to look like, but they didn't, and buying, obviously we could have bought them, but that would have been really expensive too. So I think a few freshmen had ideas for the pool noodles, and we went through a few iterations of these things because they would get blown around the lake and we would lose them, and we'd also have to like deploy them out with weights and stuff. So it wasn't a menial task. It was difficult, and it wasn't trivial to get all these obstacles built. Especially this one. This one was like a boat with a sail that would just, and we had to tow them out with kayaks when we went out to test, so that was a big deal.
Just describe what it is.
Okay, so that's the shooter challenge. So I don't know if you saw from the pictures in Hawaii, that was on a big plastic dock, and it was really set up with plywood. We made ours out of pool noodles, PVC pipe, foam insulation, and tarps and duct tape. And it would get blown around a lot. We went through a few different iterations of how to mount it to the structure, and it's a good time. This is the scan the code challenge, and it's made out of more foam and the actual LED light. Dan, did you program that? Yeah, so that was programmed to scan, like, put up a code, and the boat would detect the code that was up there and move on to the next challenge. Yep, and we had to reassemble them like every time we went out to test. This is the docking challenge that you saw in the big video. This was the biggest pain to put out. We only put it out a few times just because it's so large. You can see the person there for scale. But going out and testing with this is really valuable. Okay.
Hi, I'm Matt, and I was the lead electrical, and I had a really great team of people that helped me. So I'm hoping to grow that team for our next competition. So our electrical system had 3 key values that we used to build up our system. We emphasized redundant power supplies and sensors, and then safety, so a really comprehensive kill system. So as far as power goes, actually go back real quick. And so that's the inside of the box that Sylvie built. It has all our electronics in it, except the sensors and motors. Okay. So we had this redundant power supply system that was redundant for all the electronics other than the motors. So there were 2 batteries one on each pontoon, and each battery powered 2 thrusters, and not like the left side or the right side. It was the front and the back, and that was so if you lost the battery, you can still maneuver with the front or back set. So that was a cool thing that we did. And then it would feed the power from those 2 batteries would feed into a merge board that merged the power into one rail that was then used for all the electronics. Anything else I want to touch on? No. Okay. Yeah. We had a lot of sensors on our robot to allow it to see, mainly concentrated on our front sensor mast. So that was where we had our forward-facing cameras, our LiDAR, our side-facing camera for the shooter, and as well as our INS system. And then underwater, on the back, we had our hydrophones, which are used to find the acoustic pinger, as well as our underwater camera, and then On the back, we also had antennas and things. So the safety was, again, something we really emphasized. We had a 6-input kill system. There are 4 physical buttons on every section of on each corner of the boat. And then we had a remote kill system, which was on shore, and we could press to kill the robot. And then the robot itself could kill its own motors. So killing physically cuts power to the thrusters, and leaving all the other electronics functional. So we could figure out what went wrong before we re-enabled the system. And if the robot detected that it was no longer communicating with the shore, or that several different parameters were out of the safety zones, it would kill itself. So that was a cool innovation. And this is what the system became. Like some people talked about, we started out with a very basic system we used to put in the water the same week we got it, and it grew over time to what is shown here. And we hope to make it grow a lot more for our next competition. And here is software. Nope. Oh, I totally forgot to mention. One of our members, Forrest Voigt, graduated from UF. He started a company called Silphase, and his product is this INS, which allows you to detect your position and orientation with very high resolution. And he's developing this as a product. It's really great, and he allowed us to use it on our vehicle, and it was one of the key sensors we had. And is that it? Okay, now software.
Hi, so I'm David, and this is our software team. Right here on the left, 2 of our guys couldn't make it because they're at Uber right now. And this is the rest of our team here. So the basic architecture and toolbox that we use for our robot is this thing called ROS, stands for Robot Operating System, which Dr. Crane talked about earlier. And it basically allows us to pass messages between different executables running on the robot. It needs to be pretty modular, and it would be very complex and error-prone to try and implement our own this type of system. So we use ROS, and it works pretty well. Right here, you're seeing a ROS simulator called Gazebo, which allows us to simulate our whole environment and try to see how things would turn out at the lake. Next slide. Yeah. So our mission system for Navigator was adapted from the sub, but it had to be reworked a significant amount because we on the competitions we do for the sub, it tends to be pretty linear, where there's just a set of challenges and you can attempt them in any order. You don't really need information from one challenge to do another challenge. That was not the case for Navigator, so we had to rework the system, and it was challenging to do, but with extensive testing at Lake Wahlberg, we were able to experiment with different ways of chaining missions. If you guys ever went to Lake Wahlberg on a Saturday or Sunday this past semester, you were pretty likely to have seen it there. So right now, this is just pictures of us testing. The average student in our group spent about 140 hours at Lake Wahlberg during the weekends. So it was pretty thoroughly tested, and it really helped us in the long run in the competition to kind of build faith in our systems and kind of know what systems could be relied upon. So I worked on the acoustic system. So there was a pinger underwater which would pulse, and we were supposed to use it to guide the robot to specific mission locations. That was we didn't have other cues but the pinger, so we'd have to go through these gates that were this is what guided us to them. These are little underwater microphones which will listen to the pings and try to calculate time deltas between the difference that the pinger took in reaching one of those hydrophones versus another. When you have enough of those, you can calculate although a bit noisy, you can get a heading towards where the pinger is located. And we moved around and used parallax to get a good amount of heading observations, and used a least square solver to determine the position of the finger, and that worked pretty successfully. So there was another challenge where we had to detect some shapes underwater and report like what quadrant a certain shape was in. There was a little grid in the water, and we have to do a search pattern. So our first attempt at that was this vehicle called Anglerfish, and yeah, I pass it on to Anthony.
Hi, I worked on the simulator for the platform. We decided to go with Gazebo mainly because it's supported by ROS and integrated very cleanly with our software stack. What you can see here is actually an image of what the robot was seeing, just basically the sensor data. Gazebo allowed us to very cleanly integrate our software stack, meaning that we didn't have to change anything to simulate. We just passed in the data from the simulator as if it were the camera data or the LiDAR data. So we can test our mission systems in the simulator and verify that the logic we wrote worked before we ever went out to the lake. And while nothing can compare to our actual lake testing time, this really did help us tune things properly so that when we went out to the lake, we didn't have to debug small errors that we could have caught in the lab. Slide. Our challenge elements were all designed by the mechanical engineers, and while they weren't perfect, they were very accurate to the rules and very accurate to what we actually modeled in real life. So we had detect and deliver and scan the code here, and the scan the code actually worked like it did in real life. It actually flashed the colors and did everything you would expect. Slide. So here you can actually see the rays of the LiDAR, I think. Yeah. And this is basically what the robot was visualizing as if it were in real life seeing those obstacles.
As mentioned earlier, the competition consisted of multiple tasks that the boat would need to do autonomously. One such task is this detect and deliver. As the name implies, we had to detect a shape and then deliver a ball into one of the corresponding two holes. The way we did detection is we used open source, OpenCV, Open Computer Vision, and we would filter out images and then process and then try to find the correct corresponding shape and then color. One of the challenges we had was in Hawaii, sun conditions were pretty rough, so we had to work around that. After finding the correct shape, we would reproject the corresponding LiDAR points, and then, as you can see there, and then we would estimate a normal from those points, and then we will tell the boat to move, perpendicular to that normal, and then fire and shoot. And navigation.
Hi. So the mission and perception systems that were just discussed would basically determine where the robot needs to go, but we still have the question of how the robot is going to get there. So at this planning level, we need to basically find a sequence of states, a state trajectory between where we are and where we want to be that are feasible for the boat to take. So feasible is sometimes a simple thing to think about in the sense that we don't want to collide with anything, so there are regions that are infeasible. But there's also feasibility from a kinodynamic perspective. Our thrusters have maximum thrust outputs, and the boat itself has inertia. So if it reaches a certain top speed and it needs to stop in place to not hit an obstacle, we need to be aware of the limits on our acceleration and all of these other dynamic forces that need to be taken into account. So to handle all of these kinodynamic constraints and arbitrary obstacle constraints, we implemented a sampling-based planner called a rapidly exploring random tree. So basically, this uses kind of a Monte Carlo approach to growing this space-filling curve, where only increments that are feasible in all senses, dynamic and with respect to the world, are satisfied, and then we pick the shortest one. Go to the next slide. So as you can see here, this was a fake O-grid that we made the boat think exists. So O-grid is occupancy grid. So you can see we can pretty much draw anything. Arbitrary environments, arbitrary obstacles can be handled. This is much nicer than certain other kinodynamic planners that might require that our obstacles be confined to spherical shapes or things like that. Like potential fields-based planners require a lot more constraints. So being able to draw an arbitrary region, then the teal box that you see is a sample space. And then these samples are constructed basically using a simulation and the RRT algorithm. And then we would take this path. So you can see the yellow box representing the boat taking that path. The important thing is to understand is that these aren't just trajectories in the position space. They are actual lists of velocities that the boat wants to obtain. So then, if we go to the next slide. This was mostly to give the judges a laugh. So this is the robot navigating the Robot X challenge, literally. Next slide. So in order to track this trajectory, we've generated the trajectory, now we want to track it. Like any roboticist, you throw a PID controller at it first, right? So this is what we pretty much do on Subjugator and some of the earlier robots, because you're primarily moving a holonomic vehicle in straight line paths. And a PID controller is perfectly fine for that. Any ordinary integrator is going to close up all that steady state tracking error really fast as we adapt to simple things like the gravitational effects, the balance of buoyancy, things that are static in the world's frame. They don't change. However, in this competition, it was kind of like the first time that we really had a lot of curved path motion moving through like complex environments like those buoy fields. And what we found was that moving on tight curves, we would come out from the desired path. So we would get like this steady state error due to centripetal effects. And the centripetal force is following the boat to whatever is to its right, but that changes in the world frame. So an ordinary integrator is not sufficient to keep us along our path in curves. So to handle that, we used a model reference adaptive control architecture. Mouthful there. Basically, it's a fancy integrator. So we take a model of the boat that includes the centripetal effects because it models a full rigid body, as well as some nonlinear drag effects too. And we say that we don't know any of these parameters, but we're going to move these parameters in a way that closes steady state error, or closes tracking error. So basically, it's an online gradient descent algorithm to figure out a feed-forward term that will cancel out all of those unknown disturbances, centripetal force being an unknown disturbance. And this worked amazingly well. The boat would, first of all, sit rock solid in the water despite waves. It was kind of like, it's like elegant. You see the waves just crashing, and it's just holding there, perfectly still. And then, additionally, when moving around, tight corners and things like that, I was pretty much guaranteed, which makes me rest easy, that we would follow the paths that we wanted us to follow. Those lines that we drew before in the RRT, that was just what we wanted to follow. How well would we track those? We tracked them very well.
So besides our extensive testing and our simulation, one way that we're confident in our code that it's bug-free is through our use of collaboration tools. And all of our software that we develop in Mail is open source. And that's not just we put a zip file on Dropbox every 6 months. Like, we really do develop it in an open source way. And that means that before any code gets pushed onto a robot, it goes through this review process where everyone on the software team has an opportunity to look at the code, try to find any sort of mistakes that might be in it or unthought of edge cases, and they can comment on it. It's also automatically tested. So we have a continuous integration system that will build our code and run certain tests on it, just to verify that when we change our code, we're not introducing bugs or regressing in any way.
And here at Team Navigator, we feel like we've been given a great opportunity to be able to participate in competitions like RobotX. And we feel like we also have an obligation to extend those opportunities to the next generation of engineers. In 2015, at the RoboBoat competition, we were awarded the Outreach Award, as well as $1,000 for our efforts. And that money was spent at a national scale. We invested some of the money to a STEAM camp, so that's science, technology, engineering, art, and math, and for a camp for the Citizen Potawatomi Nation over in Oklahoma. And then the rest of the money was used for a STEAM festival on the Navajo Nation. But we also do a lot of local outreach as well. And so one of the things that we do is some of the team members have invested a lot of time with the local high school robotics teams. So we mentor these students. This is one of the local teams. This is PK Young, just down the street here in Gainesville, Florida. And we've also have a really good relationship with a team out in Tallahassee, the Lionators. And not only is this a good experience for the high school students, because it allows them to become familiar with engineering at a high school, in high school, but it also really helps our lab with sustainability. This last year, 3 of those students from those 2 teams came in as freshmen, and they were able to contribute at a very high level despite the fact that it was their first semester at the University of Florida. And between those 3 students, they developed all the hardware and all the software for 2 of the challenges. The 2 being the Detect and Deliver, so the racquetball launcher challenge, as well as the docking challenge.
Of course, none of this would have been possible without the support of our faculty advisors and some other key players. Dr. Schwartz and Dr. Crane helped us out by providing fiscal support, some words of wisdom from other projects, and access to facilities and equipment on campus. Dr. Hill and Shannon Ridgway also were able to help us. Dr. Hill was able to get us over some humps in software, and Shannon saved a lot of money in terms of lost hardware by providing some tips ahead of usage. We also had two other students, Daniel Duggar and John Esposito, who weren't able to travel to Hawaii with us. However, in our getting ready for Hawaii, they helped us out extensively. Now, before we were able to compete in the Robot X competition, we had to get a boat first. And so we spent a lot of time coming up with a large document that we submitted to the course coordinator justifying why we deserve to compete in this competition. And the coordinator actually flew out, the representative, she flew out and interviewed us and decided that, hey, you guys are pretty serious, so we're going to give you a boat. And so they shipped it in this huge crate, weighed about 1,500 pounds. Had to get Mike Braddock on the forklift to pull it out. We were so excited when we got it. We put it together right outside on the street there, and within 1 week, we had our plywood platform, Tupperware containers, and everything on it. Had it in the water on its maiden voyage. Lake Waburg, and here's us pushing it off in the water for the first time. Notice there's only 2 thrusters on the back. At the time, we weren't sure what we were going to do with the thruster configuration, so we went with a simple skid steer system. And then within about an hour, it didn't work, and our lead electrical here had to jump in the water and rescue it before we brought it back. And the errors continued to happen, but in less frequency as we progressed, spent more and more time at Lake Waburg, got more comfortable with systems, came up with new iterative designs that were improvements on other designs. We had a pretty good setup at Lake Waburg. Dr. Crane allowed us to use his trailer. Here's the software team working inside with the door down. We have our radar antenna there, and also the truck with trailer. One thing you'll notice, this is early on in our testing because we didn't trust the vehicle yet, so we had the door down so we could watch the boat while we were testing it. However, as the days and months passed, we got more and more confidence in the system, so we actually ended up closing it. We couldn't even physically see the boat because we were so confident in our cameras and in our sensors, and so we could really enjoy the AC units on top. But we didn't just do the testing at the lake, so there's a lot of idle time down there, so we thought, well, how else can we utilize this time? So a lot of students learned how to do surveying. So they took these, this is Kip and Matt here, and they're using GPS and a compass and some binoculars to shoot bearings. And then when they find where the bearings intersect, and that can actually give us a rough estimate of the GPS coordinates of objects. So when we got to Hawaii, we knew, hey, I can ahead of time, I can get course coordinates of where these challenges are, and then feed that to the software team who can give that to the boat to say, hey, search in this area for this obstacle, because at the competition they do not give us the GPS coordinates of the challenges. We were at the lakes for about 8 to 10 hours every day, so people get hungry. So we brought out our smoker, and every time we were out there cooking sausages, pulled pork, chicken, you name it, had a lot of fun. It was just a really good time. And all this workup, spending time at the lakes, learning how to do ground surveying, getting confidence in the platform, setting up the course, breaking down the course, taking the boat apart, putting it back together, got us ready so that when we got to Hawaii, we were ready to compete against these veterans. In the challenge of the 8 finalists that made us, 7 of the 8, excluding us, were veterans from the previous competition, meaning they had had their boat for 3 years before us. They competed in the 2014 competition. So we were competing against some very seasoned teams at that time. Here's a picture of the software team working. You kind of see the cramped environment. They have the small table here, 5 laptops, 6 laptops on there. And it's windy, it's hot. We're up early, we're up late. And sometimes it can be a pretty hostile environment. Here's the boat heading out to an ominous storm that's approaching. You can kind of see the waves coming up. But it all paid off, like I said, and we ended up coming out on top, winning $25,000 total. About this time, they started talking about the next competition. So it's biannual, so this is 2016. The next one's going to be 2018. It's going to be held in Hawaii again. But some things we can expect them to have. They're going to put a bigger emphasis on underwater vehicles. So you can see one of the team's underwater vehicles and conducting these tasks. They may bring aircraft again. So the vehicle would launch an aircraft, and the aircraft would conduct some mission searching out ahead of time. So we need to start preparing for this now. We're less than 2 years out, about 18 months out. So some of the improvements we can do on the boat or our team is improving anglerfish. So anglerfish is a acrylic tube with a 3D printed structure on the outside, and I'm really glad I didn't bring it because some of the other teams who had 3D printed submarines were destroyed by banging around inside the seas. There are really high, rough currents and winds. So this needs to be redone, probably a whole new sub, and the programmers for it, we need people to program that sub, and the electricals to build electronics for that. Another improvement for a boat, and these are just very coarse. There's other things, but these are kind of the highlights. Our thruster mounts, they seem really simple, but we spent a lot of time banging our heads on it, and these are only temporary solutions. These things would wear out about 40 hours of usage, and we'd have to replace all the hardware again. We never really came up with a good solution because we ran out of time, but these are kind of good enough. So now that we're in downtime, this would be a great time to go revisit this, figure out how to make these better. Now, Kip spent a lot of time on his racquetball launcher, but he wants to take it to the next level and creating a new actuated racquetball launcher. So the first racquetball launcher was fixed, meaning we had to move the boat to get that arc of the racquetball into it. The launcher was fixed. So this is an actuated one. This is actually Embry-Riddle, one of our competitors, but they had a cool design that kind of inspired us. And it's also, instead of doing spinning discs, they do pneumatics. So need electrical to work on that too, and also software to program. But having it actuated with a camera, a lot more effective. We don't have to be as close or as, we can be a little sloppier with our approach to it. Also the electrical overhaul, so Matt talked about this inside of the box again. A lot of wires going on there. That could definitely be overhauled. We'll decide whether we want to keep using water cooling. It was kind of a pain, or move from something else from that. Also coming up with an improved wireless kill. So this is a circuit board. So those of you who enjoy building PCBs, how we killed our boat was actually through a laptop, through an Xbox controller. So the Xbox controller had to be relatively close, within 30 feet of the laptop, and the laptop had to be hardwired to our antenna. And so the antenna had to be battery powered. So we had what's called the octopus, where we'd have one person hold the laptop, one person drive the boat with an Xbox, one person hold the antenna, and then sometimes we usually have a second laptop that was also wired to the antenna that would be recording data on the boat as we transition from point to point. And we're walking a half mile, 3/4 miles from course 1 to course 2, course 3. It's a very big course this year. So this system would completely remove the laptop necessary. It's a completely different wireless communication command. So we wouldn't need the laptops also. So the software team could run to the set, get set up, while the remote control guy could drive with him or just one other person all by himself. And that concludes our talk. Are there any questions? Questions about the platform? Questions about the competition?
South Korea had four thrusters, like where we put ours, but they're all pointing forward, and then they had two, perpendicular to those for strafing. So they had the same kind of holonomic control that we're capable of. But yeah, when kind of going around talking to the teams, hearing different ways that they approach these kinds of problems, you kind of get like a new perspective. Like, I never really saw that approach to what you're doing, and me and Forrest were kind of walking around talking to people, and for the most part, we kind of disagreed with the way they were doing things. So yeah, there's certainly a way that we do our robots in Mill, and I was actually thinking about possibly having another talk where I might go into like more technical detail about exactly what we do, how we do our robots in Mill with multiple thrusters, to pass down that knowledge so that you guys can come in and keep that kind of trick going.
Yeah, and I think that's one of the reasons why we won too, was because the last day of the finals on Sunday had some of the worst weather the whole week. It was raining, it was very windy, and we, because of Jason's controller and the layout of it, our boat did very, very well in the weather, better than any other team, and I honestly believe that's one of the factors why we won that year.
Yeah, it's really hard to like pinpoint, one thing, because you can take anything out and just basically make us fail the competition. If we didn't have perception, you didn't get points for hanging out in the water. Holding steady in the wind didn't get you points. It was just cool. So it was really the ability to go from place to place and do perception. For example, we docked, and that gave us a huge amount of points. So it was one thing to be able to move into a tight dock while the waves were going, but it was another thing to be able to see the shapes and pick the dock correctly in these conditions that were just like very arbitrary lighting. It's hard to even tell the colors just from like looking at them in person. So it all goes into play. Any system could fail. Yeah, a motor could fall off if a mount wasn't designed correctly. It would fail.
Yes. Oh yeah. So the company starting is called Silphase. He graduated just last year, Forrest Voigt. So he came with us. We make it sound like it's this like external thing that he gave to us, but realistically, Navigator was a test platform for him. He was coming to every one of our testing days, looking at the data that he was collecting, and there were problems that we found with it along the way. Not many, but some. Basically, like it was a symbiotic relationship where we would get state estimation from his device, and he would get lots of data and proof of concept for his company. Yeah, I mean, he's not like mass producing them yet, but at some point he will, and his target market are roboticists, like hobbyists. He's trying to outsell the military contractor companies that will sell you a box this big GPS INS for like $30,000. So it helps to have some sort of skill ahead of time. We get a lot of students who know Arduino, mechanicals who know SolidWorks, and programmers who may know Python or C++. Those are really good, and they'll get you ahead of the game. You'll be able to contribute more quickly. But because we use ROS is not as popular amongst new programmers. So that's usually, if you're going the software route, we're going to point you towards ROS, which is pretty intimidating because it's very general, it's very wide, and there's a lot of things to learn. But what we found, the most successful students in our lab, all the students here, may not necessarily have started here with some particular skill. So don't think that, oh, I don't know how to program Python, so I'll never be able to work. That's not true. It really comes down to a mentality, and do you really want to participate in these projects? Because we do put a lot of time into this, on top of classes. It's all volunteer. We don't get course credit for this. We don't get paid for it. You don't get paid research. We just really, really like this stuff, and we like building, and we like competing. And so it's driven from inner. And then, over maybe a year, maybe 6 months, depending on how quickly you will be directly contributing to these projects. But we can always use people. If you don't know how to do anything, when we go with this testing, it's a lot of effort to drag these things, drag the boat, drag the sub to the pool, get that set up. And then in doing that, you get exposed to the testing process, and you can ask questions. Hey, David, what is that RViz thing? What is that? What are you guys doing right now? What's this PID thing you guys say about all the time? Things like that. That's kind of how you get exposed. That's how I got involved. I did some Arduino. I could do some circuit building, but that was really it. And just being involved, like, hey, that's really interesting to me. I want to learn a little bit about that. And then it took off from there. And before you knew it, I was taking over entire projects. Right now, we're not going to have any scheduled meetings. And the meetings we do have are not, they're kind of shoot from the hip, like, hey, we need to do a meeting tonight kind of stuff. But we're open right now. I mean, if you talk with Dr. Schwartz, talk with Dr. Schwartz, say, hey, how can I get involved? And then Dr. Schwartz will point you in the right direction. If you want to work on the sub, you'll be working with these guys right here, which is an active project right now. Navigator is kind of in the background right now. They've taken the software from Navigator, regurgitated it, and now are refining it for the second time. And then when we start up Navigator for the next 2018 competition, we'll be taking Sub 8 again and putting it back on there. Yes? How was Hawaii?
Dude, it was amazing. It was amazing.
I didn't get to enjoy it, and not many people got to enjoy it. It was. They did, but yeah.
They're comparable.
Yeah, well, I'm biased. I grew up in San Diego, so but Hawaii's nice. You start getting outside of the main area, and there's a lot of slums. There's some slums. The weather's beautiful. Beaches are beautiful. It's very, very, very crowded. It's like New York City crowded. It's pretty bad.
We were in Honolulu, to be clear.
Right. I mean, if you get out, and some people, like Matt, went to the actual island of Hawaii, where there's very, very remote, and so that's the place to go. But you can't fly into there directly. You have to fly into Oahu and then get a puddle hopper to the other airport. So, and that's where they filmed Lost and all that stuff. Was in the main island.
Yeah, it's tough. We had 18 students there for 13 days, and then that was what I paid for. And then a lot of them stayed within 5 extra days, after 12 days. One student stayed there for 3 extra months. He came back.
Okay.
He didn't want to come back, but he came back.
There were a lot more hands before.
Okay, so if you want to get involved, send me an email. Send me an email, come visit me, not this week, next week, or the week after. If you want to do something in the summer, if you want to start the fall, please come to me. Usually Monday, Wednesday, and Friday afternoons I'm available. So I'm in, we're all in mechanical engineering, mechanical aerospace, building city. And if you go in there, there's signs and places like that. So come visit. You put mill.ufl.edu or Navigator US or Subjugator, you'll come up with that. Right now, it's sub and boat. Sub and boat. Now, we've done IEEE stuff before and we're doing a little bit, but it's sub and boat. And that's what we do now. We don't have enough. We don't do the other robots. Aggregator, is that's the Lunabot used to be called Lunabot, but that's I'm an advisor of the team robotics, but Mike Gibb is the advisor of that part. We do robotics.
We don't have enough manpower to do more than this.
We don't have manpower or room. In fact, the only way we can do this boat project is because we need Sidewire's garage to have their boat. It's a high day, it's a nice room, very nice room, and it's very clean as opposed to mill.
Answer your question though, the really active one right now is Subjugator.
I feel like they're always going to be like flip-flopping. Robo sub is going to happen, and then it comes back to boat, and then when boat is over, it goes back to.
It's for the boat team, I think 97%, all that's doing is one player, two-player lab is on the boat team. And now he's on the sub team, and I think he'll do it on the boat team. And pretty much the whole team goes to one project. It doesn't have to be that way, but that's how it is. There's so much to cover. When they build a circuit board for the boat, hey, it's almost the same, it's a little smaller and stuff. And certainly the software is made to be cross-platform software. And the control still. So they learn what you learn on one, you can learn on one. Now, when we're talking about cell phase, the original prototype of the INS that Forrest made was on our first robot boat. We found the need, and we started building it there. And so version Alpha was on Propagator, and version Beta was on Navigator. And also, while we were out there, Hawaii, the first day out there, University of Hawaii, they could not, their INS wasn't working. So Forrest heard, he went over there and said, hey, have mine. And about an hour or two later, their boat was probably the second most controlled as far as knowing where it is. And so that's the University of Hawaii logo. They have one of his units. And 6 months from now, you buy a unit for, what did you say, about a 20th of the price of an equivalent unit from one of the big companies. I don't know what he'll sell it for. I think he said $750 or something. Well, it's on his website. It says $750 on his website. So, anyway. But he was on our sub-team and our boat teams for years. He started as a freshman, like 3 of these guys here started as a freshman. And we had a guy graduate about 2 years ago. He started as a freshman, and he went all the way through his PhD, and he's working at the Naval Research Lab right now. He was the sub-team leader for many years, and got his whole PhD paid for in his last year of undergrad, saved up a lot of money because they paid him salary as well, and then went to work doing exactly what he's doing, what he was doing at Mill. And the head of the submarine competition, the guy who makes the rules, the technical director, was the leader of our first sub-team. Came from SIMAR, was the leader of the first sub-team. The guy that's the technical director of Maritime Robot X was on the first sub-team also, an electrical student in Mill, way back at the beginning. So the only thing that we don't run is RoboBoat. That's run by a student who went to a very good team for submarines, ETS, a Canadian university, and he got his PhD at Cornell, and he wanted to start something new. And so, but we got people everywhere. Former Mill and SIMAR guys are at any place you want to be. What's that, a commercial? Any place you want to be, our people are there now. University of Florida students rock. Do some real projects. You're a super rock star, not just a rocker, a star. Okay. Anything more? Okay, come visit us.